Hi, I'd like to discuss our open source leg project as part of the IROS workshop, State of the Art in Robotic Leg Prostheses, where we are and where we want to be. I'm Rouse. I'm an assistant professor at the University of Michigan, and I direct the Neurobionics lab. This work is led by Dr. Alejandro Azacar, a former PhD student in my research group, and Unhee Lee, a current PhD candidate. Control is one of the greatest barriers affecting the widespread success of robotic leg prostheses. It's one of the main reasons why you don't see a robotic leg prosthesis in the public. You may see upper limb prostheses, but very rarely a lower limb prosthesis. One of the challenges for lower limb prostheses is that they have to support the body. So any errors in control can cause serious injury or cause someone to fall down a set of stairs, for example. So this near perfect benchmark for control has really created a lot of challenge in creating control strategies that can be translated to the public. Fortunately, we have many talented researchers around the world studying the control of robotic leg prostheses. But before they can test their control strategies, they first have to have a robotic leg on which to test. They can't typically buy a commercially available powered prosthesis. There are two available because we don't have access to their controller settings. So instead, each group is forced to build their own prosthesis first. And this presents two challenges. Firstly, it's incredibly inefficient because we're spending hundreds of thousands of dollars and years to develop these systems over and over and over again. And secondly, it presents a challenge of comparing across different control strategies because it's difficult to decouple the results that stem from the hardware versus the control. And if you look at the prostheses on the screen, you can tell they have very different properties. They have different masses and mass distributions, tethered versus untethered operation, different power characteristics and transmission ratios, and all of these factors affect the control strategies. Our solution is to develop an open source robotic leg that's available to the research community. Our system is modular, so it can be used as a knee or ankle separately, or together as a full robotic leg. If we look under the hood, there's a few things I'd like to draw your attention to. Firstly, is we leverage technologies that were developed by the drone industry, specifically the brushless motors we use. Drones don't have transmissions because of the added mass, so to produce the torque needed, motors for the drone industry have gotten wider and thinner and operate at much lower speeds. The greater torque capacity for these motors enabled us to lower the transmission ratio and leverage belt drive transmissions, which are quiet, efficient, and low cost. They also don't have the long lead times or high price tags associated with precision machine components. We've also integrated sensing into the design. There's a 6-axis load cell that can be included. There's IMUs on each degree of freedom. There's motor encoders and joint encoders and motor electrical information, including motor current and voltage. And together, this information provides a customizable sensor set that can be used for different researchers studying different control approaches. We have onboard battery and control software and hardware, so the system can go outside the lab, it's untethered. And we have a series elastic actuator that we've implemented in the knee prosthesis to help researchers who need high fidelity torque control. And I'll talk about that for just a moment. Series elastic actuators are an approach for robotics that were developed around the mid to late 90s. The idea is to place an elastic element between the output of the transmission and the load. The deflection of the elastic element can be sensed and used along with its stiffness coefficient to calculate torque. And this has many benefits. Series elastic actuators have improved torque sensing and torque fidelity, better energy storage and return, and improved shock tolerance. But it comes at a cost. Series elastic actuators have reduced force or torque bandwidth, and they also have significantly increased mass and complexity. So our field is really split on this issue, where some researchers and designers like to implement series elastic actuators, while some researchers avoid it. And we've thought a design that would be able to be used by both groups. We developed a compact and high displacement torsion spring that fits around the axis of the knee. The spring is a disc, and it's 24 individually spaced radial cantilever beams. And those cantilever beams intersect with the involute profile of a gear through rolling contact. To give you an idea of what interacting with the spring looks like, here's a video of me kind of interacting with one on my desk. You can see as I push down on it, it rotates that gear, which deflects the individual cantilever beams. These discs can be used in parallel, and they can be stacked within the design, enabling settings between 0 or infinite stiffness and 6 spring discs. Each disc has a stiffness that's about 100 Newton meters per radian. So this allows researchers who would like to implement series elastic actuators to customize the elasticity based on their control needs. And it also enables researchers who do not like to use series elastic actuators to use a rigid system. To give you an idea of how we implemented it in the design, this is a cutaway view of the knee prosthesis. And we're going to look at the output of the knee joint. Inside the pulley on the last stage of the timing belt fits 6 of these discs if they're installed. So the discs can be installed upon assembly, and anywhere between 0 and 6 discs can be installed. This enabled us to add series elasticity with very minimal weight and volume increases. I'd like to give you just a quick overview of the design process used in developing the open source leg, the details of which are provided in the publication that's referenced at the bottom of the screen. We begin with a target subject's mass and use this information to calculate joint velocity and joint torque profiles for different activities obtained from the biomechanics literature. We then convert this to the motor velocity and motor torque requirements using the transmission ratio and transmission efficiency. We use motor velocity and motor torque to calculate the motor's voltage and current around the Q-axis, using the phase inductance, phase resistance, and motor Q-axis torque constant. We use the current and the phase resistance to calculate thermal losses and estimate the increase in winding temperature to ensure that it maintains within the permissible range. And simultaneously, we're investigating the physical design, so the housing and structural support, protection of the transmission. And this all occurs in a cycle where we investigate transmission ratios, different motors, different support conditions, and the cycle guided our design and ultimately led to the open source leg that we have today. Following design and manufacture, we tested the control performance for different controller types, beginning with position control. We tested step response tests where we looked at the controller performance and its ability to track steps of different amplitudes ranging from 5 to 15 degrees. We also tested the controller's frequency response by having the systems track a position profile that was filtered Gaussian white noise. We looked at different noise profiles that had a maximum value also of 5, 10, and 15 degrees. We used this information coupled with non-parametric system identification to get the frequency response Bode plots that are shown on the screen. If we use this information, both in the time and frequency domains, we can determine the controller performance for the open source leg in position control. The rise time was 26 milliseconds, the overshoot was 2.4%, had about 0.9% steady state error, and the bandwidth was between 10 and 20 Hertz, depending on the amplitude. We also performed an analogous test of the system's current controller, and in this test, the knee and ankle were held rigidly in a testing setup. We tested the time domain response by having the systems track a step response in Q-axis current up to about 3.5 amps. In addition, we obtained the frequency response by having the systems track a filtered Gaussian white noise signal with a maximum amplitude of also to about 3.5 amps. And if we use this information, we can determine the time and frequency domain characteristics of the system's current controller, where the rise time was about 29 milliseconds, overshoot in this case was 18.5%, had basically no steady state error, and the bandwidth for the current controller was about 200 or greater than 200 Hertz. And the high performance of the current controller really stems from the differences in the electromechanical delays of the motor compared to the physical system. We also developed a closed loop torque controller, and rather than show you plots in the time and frequency domain, I'd like to show you a little bit more of an intuitive robotics test. Here we're closing around a zero torque reference, and we're closing the torque loop around the load cell that's sort of seen in the bottom of the knee prosthesis. And as you can see, we're able to obtain relatively high performance using the load cell, where Unhi, who's interacting with the open source leg with a wrist cracker, is able to interact with it without breaking the cracker. I'd like to conclude by telling you a little bit about what it's like working with the open source leg. Our system receives control commands from a high-level computer, and we use a Raspberry Pi. The control commands are sent via a set of open source Python-based APIs that were developed as part of this project. This enables researchers to get up and running very quickly. In fact, I would recommend that you watch the demo video that's kind of the partner video that's in this IROS workshop. It includes an explanation of a lot of the hardware and software tools used to control the open source leg. Everything for the project is freely available on opensourceleg.com, and I would encourage you to check it out. And what I'm particularly excited about is that the open source leg is really intended to be a tool for the community. And we have up to 8 institutions currently using the open source light around the world. I'm very excited about that. Thank you for watching our presentation for the IROS workshop. I hope you check out the demo video also. I'd like to thank Alejandro and Angie for their hard work on this project, and the National Science Foundation's National Robotics Initiative for sponsoring it. Thank you.